Hello students, and welcome back once again to the world of water and the impurities present in it. In our previous video we had learned about the internal treatment of water, and in the internal treatment we have discussed about the carbonate conditioning first, and then we talked about phosphate conditioning and the conditions under which these two processes can be used. In today's video, we will learn about another type of internal treatment method, and that is the Calgon conditioning. Okay, so we have discussed about carbonate conditioning, in which carbonate ions were used. We have also talked about phosphate conditioning, in which we took the help of phosphate ions to prevent the formation of scale. Today we will learn about Calgon conditioning, in which we will take the help of a substance which is commercially called as Calgon. So let's proceed further. Okay guys, so let's see what Calgon conditioning is and what does it involves. What chemical do we select here to help us prevent the formation of scale? So for Calgon conditioning we take Calgon. The commercial name of this substance is Calgon, but chemically it is called as sodium hexametaphosphate. So we take the help of sodium hexametaphosphate, also known as Calgon commercially. So to start with Calgon conditioning, let's write down the name of the substance that we use in this process, that is called as Calgon. And remember, Calgon is the commercial name. So you can go out in the market and ask for Calgon. Okay. As a chemist, as an engineer, we need to know the technical or the chemical name of this substance, because then only we will able to learn what chemistry is actually taking place, what is the role of the substance here, of the compound here. So chemically it is called as sodium hexametaphosphate. So students, you need to learn the chemical name of the Calgon. Okay, so Calgon is actually sodium hexametaphosphate. So let's try to write down the chemical formula from the name. So it says sodium hexametaphosphate. So that means we have sodium atom in it. Okay, so I write sodium. Okay, now hexa. Okay, metaphosphate. Okay, so it goes like Na2 Na4. okay, that makes it 6 sodium in all. Now metaphosphate PO3, and since it is hexa, so I just do whole 6 of it. So Na2 Na4 PO3 whole 6, this is nothing else but Calgon, sodium hexametaphosphate. Okay, now this chemical actually is added to the boiler water to prevent the scale formation. Okay, fine. So how do we do that? Calgon actually converts the scale forming impurity into the soluble complex. Let's see how it works. So this is calcium. Okay, when we add it to water, it actually gives us sodium ions. Okay, fine, and Na4 PO3 whole 6. Okay, so it's a complex compound, so I have these ions in water. Now what happens when this anion comes into the water? It actually comes across the hardness causing salt present in water, and that salt, let's say, is calcium sulfate. You remember one of the nuisance creating salt we discussed in carbonate conditioning, responsible for the formation of scale. Yes. Okay, so when this is added to water, it gives, when the Calgon is added to the water, it gives us these ions, and the anion of them comes across the calcium sulfate and converts that calcium sulfate into CO2 PO3 whole 6 and minus 2. Okay, plus definitely Na2SO4 will be formed. Now this is a soluble complex. Okay, soluble complex. So calcium is converted into a phosphate, which actually is soluble in water. Okay, so here what is happening? The scale formation is prevented by the conversion of this calcium sulfate into a soluble complex. So when the soluble complex is formed, definitely no deposition, no precipitation will be taking place, and we say we are free from the scale formation. So students, now we know what is Calgon and where and when to use it. Let's write down the formula again. It is Na2 Na4 PO3 whole 6. This is nothing else but Calgon, and we add this Calgon to the boiler water. What amount of it is added? Okay, we take 0.5 to 5 ppm of Calgon to add into water. Now this much amount of Calgon prevents the scale formation in either of the two ways. And what are those? The ways depend actually on the type of boiler we are using. You know that we have high pressure and low pressure boilers. Okay, so what happens under these two conditions? At low pressure, if we discuss about one of the type of boiler, at low temperature and pressure, that means we are talking about the low temperature and pressure boilers. What happens in that case? When we add Calgon to the water, it forms quite a stable and a soluble complex that we discussed, and that complex is formed with the calcium salt. So a stable and a soluble complex is formed, okay, in case of low pressure boilers. But what happens in case of high pressure boilers? So at high temperature and pressure, that means in case of high pressure boilers, actually what happens, a two-step reaction occurs. If you remember in the previous slide, we came across the chemical reaction, how Calgon removes the calcium sulfate, and it was a simple one-step reaction in which a soluble complex is formed. That story goes for the low pressure boilers. Okay, in case of high pressure boilers, a two-step reaction occurs. Now let's see what and how does that occur. Actually what happens, this Calgon Na2 Na4 PO3 whole 6, okay, it actually in the presence of water get converted into Na2 P2O7 plus hydrogen gas is evolved. Okay, so Calgon is converted into sodium orthophosphate. Okay, this is what? This is sodium orthophosphate. Okay, so Calgon is converted first into sodium orthophosphate. Now this sodium orthophosphate actually comes across calcium sulfate. Okay, and when it comes across calcium sulfate, it converts it into CaP2O7, and along with that we have sodium sulfate. Okay, now what is this CaP2O7? This is technically called as calcium orthophosphate. Okay, fine. And this actually is a loose mass of precipitate. It's a precipitate. Okay, so here what is happening? In case of high temperature and pressure boilers, Calgon is converted into sodium orthophosphate. This is our first step, let's say. Okay, and then this sodium orthophosphate reacts with calcium salt to form calcium orthophosphate, which is actually a loose mass of precipitate. Okay, so we can say that this comes out to be as our second step. Okay, now this calcium orthophosphate appears as a loose sludge, and therefore you know it very well. It's very easy for us to remove the loose sludge by the blowdown operation. That is the entire story of Calgon conditioning. But there is a limitation of this process. Like we had the limitation of carbonate conditioning. What was that? It cannot be used in high pressure boilers. So here also we have a limitation for the Calgon conditioning. What is that? Calgon conditioning is not applicable for the prevention of iron oxide and copper depositions. Calgon conditioning is not applicable for the prevention of iron oxide and copper deposition. This simply means that if my water, my boiler feed water is having, let's say, iron and or copper impurities, okay, so in that case we cannot avoid the deposition of these salts, the precipitate of iron salt, the precipitate of copper salt. We cannot prevent their deposition on the inner wall of the boiler by this particular method. So here it fails actually. If iron or copper impurities are present, if iron oxide is present in water, we cannot prevent its deposition on the inner wall of the boiler by using Calgon. So there's a remedy to that also. In such cases where iron oxide and copper depositions can take place or these salts are present in water, they can be prevented by adding EDTA. If you remember, EDTA is very good at making complex with the iron, making complex with the copper. Okay, so these can be prevented by addition of EDTA or the sodium salt to the boiler water, or you can add the sodium salt of EDTA, disodium salt of EDTA to the boiler water. And what does it do? It goes and makes a complex with the copper or iron over there. Okay, so in a way you are preventing the formation of scale by the iron and copper salts. How? By letting them forming a complex with EDTA, which is a soluble one. So in this method, the problem causing cations are converted into the complexes, EDTA complex or EDTA metal ion complex, which actually stays in the dissolved state. In other words, these are the soluble complexes. Okay, so they stay in the dissolved form in water, and so they do not cause any harm. So that's how this limitation of Calgon conditioning can be overcome. But overall, if these iron oxide or copper salts are not present in water, then their Calgon can do a good job for us.